So, what do we know now about the balance of electromagnetic radiation? We know that there's a cycle called the Chapman cycle that balances that. And that Chapman cycle is what produces ozone. And we know that ozone and oxygen in the stratosphere is what basically allows a certain amount of electromagnetic radiation to penetrate into the earth and filters out the other. We know that ozone layer and oxygen in the stratosphere filters out completely UVC, then partially on UVB, and then on the minor on UVA. So essentially we have UVA and B entering into the troposphere, which is where people live and where we live. Now, so the ozone basically protects us when it comes to UV irradiation. All right. So slide 21 then shows us something very interesting and troublesome, actually, in that there is this hole in the ozone. All right. That is a scientific fact. That is not a myth. That is not an Al Gore conspiracy or someone else's conspiracy. There is a hole in the ozone. All right. And what we're finding is that the growth of that hole is faster than can be predicted by natural occurrences. So let's take a look here and read the verbiage on slide 21, and then we'll look at the slides and we'll explain that further. All right. So what we're talking about now is upsetting the natural balance. When we upset the natural balance, that leads to ozone destruction. All right. So again, we know the ozone layer provides natural source of protection against harmful UVB radiation. Again, this is slide 21. We know, but there's some interesting chemistry that occurs in the ozone layer that's actually part of nature, and nature can account for this. Water can basically be dissociated into two radical species. One's hydrogen and the other one's oxygen. This is part of nature, and this has been occurring since the dawn of time, as best we could tell, in terms of the ozone layer. So that's part of the cycle. That actually depletes ozone, but the rate at which it depletes ozone is not significantly faster than the regeneration of ozone. So you get it? So in other words, if the ozone layer is attacked by hydrogen radicals and oxygen and hydroxyl radicals from water, nature can take care of that. It can fix itself using the Chapman cycle. However, when we look at the rate of decay of the ozone layer, it appears that there are other species that are affected at an alarming rate. Okay? It doesn't appear to be natural. All right? So what could it be? That brings us to slide 22. It has been found that one of the biggest sources of depletion of the ozone layer has been chlorine radicals. This can be measured scientifically, and it's well known that they are there. All right? Now, this chlorine radical, again, when you see radical, that means it's a bad actor. That means it's going to cause some problem. This chlorine radical basically takes out the ozone, okay, from the stratosphere. All right? But the source of the chlorine radical is from what's called CFCs. And what are CFCs? CFCs are non-toxic, non-flammable, inexpensive, and widely available. They're used as refrigerants. They basically replace ammonia in refrigerants. And it was a really cool invention, and it really kind of revolutionized the refrigerant industry. But what the scientists didn't know was that when these materials are released into the environment, they basically go into the atmosphere and they produce these chlorine radicals. And these radicals are extremely harmful to the ozone layer. Okay, and so CFCs are contributing to the degradation of the ozone layer. That's a take-home point. That's what you want to make sure you remember. CFCs contribute to the destruction of the ozone layer. And they do it by production of what's called chlorine radicals. Now, let's take a look at the diagram on the left side of slide 21, chlorofluorocarbons. We're looking at CFCs. We have a chlorofluorocarbon here, okay? And you see it's the fluorine and it has chlorine. And when photons, and we know the source of photons are what? Right, sunlight. So when these get up into the atmosphere, into the troposphere, go up into the stratosphere, they get essentially zapped by sunlight, which is photons, frequency match at 220 nanometers, and it breaks into two radicals. And these are radicals. Radicals are basically highly reactive species, and once they're made, they try to find a way to satisfy their thirst for an additional electron, and in doing so, the chlorine attacks ozone, and it starts essentially a chain reaction with ozone in the atmosphere. And so we get this chloride radical, and this chloride radical hangs around, and it is more destructive, and it destroys at a higher rate than the natural occurring radicals formed from water, and that's important. So yes, nature itself does affect the ozone layer, but its rate of effect on the ozone layer is nowhere near that of these chloride radicals. If you take a look at this graph, and this has been studied, excuse me, if you note the stratospheric chloride, okay, that's chlorine in the stratosphere. When it's down, ozone is up. Okay, you see that? Notice if you look at the bottom red line, it's flat, starting at about 60 in 19. I think these are. I'm sorry, 19. When you look at it, okay, at 63 degrees, and then up to 68, it's almost flat. All right. Then you notice right about 68, it starts to go up, and then the red line goes up. Okay, when the red line went up, notice also that the blue line came down. The blue line represents stratospheric ozone. You don't want to see that. Essentially, you want your blue line to stay up. That's what's healthy, and right now, what's happening in the ozone is unhealthy. All right? So, we now know, and it's very clear that there is a hole in the ozone. We saw it on slide 20. We look at the graphs on slide 20. You note that the blue area in 2008 on slide 20, looking at upsetting the natural balance. And you look at 1998, it had a hole, 1988, and 1979. This is pretty dramatic, okay? You note the graph on slide 21. It starts high, and it goes down in terms of the DU, and you know the DU, the Dobson units. It's how we measure ozone. You've already learned that. And so the numbers are going down. So the fact that this graph is going down is not good. It's telling us that there is a hole in the ozone. Okay? We can look at this another way when we look at the ozone hole on slide 22. Why over Antarctica? Well, as it turns out, Antarctica is just by nature happens to be a very good laboratory where these radicals can produce themselves and hang around long enough to be destructive. Okay, its temperatures and the polar winds are just right to create an environment where these radicals can be destructive. All right, just reading the verbiage, the lowest stratosphere over the South Pole is the coldest spot on Earth. So we see that if you look at the graph, you notice here the blue lines down and the yellow, the red line goes down, and it kind of shows the Arctic winter about July, August. You don't want to be there then. You want to go to Florida during that time. So it's really cold, and that cold condition, all right, the coldest polar stratospheric clouds will help support the chemical reaction that produce active chlorine that catalyze ozone destruction. So here's the type question I tend to ask on the exam. Why is the hole over the ozone? The answer is because the polar winds and the cold temperatures favor good production of the radicals, specifically chlorine radical, that catalyzes destruction of the ozone layer. All right? Another way of looking at this, at the hole, and where do we go from here and what do we do? Well, a global corporation resulted in the Montreal Protocol of 1987, and this is a question I'll ask on all my exams. Okay, I just like this. I like for us to be aware of this particular regulation. The Montreal Protocol set in place some standards that force most of industry, well, all of industry, frankly, well, we'll say most of industry, certainly in the United States and North America, to regulate CFCs. And because of that, that brought the level of chloride in the atmosphere down, and it caused the ozone to go back up. And if you look at the top graph, between about 1965 and about 1995, and certainly let's say after 1970, the red line being up high, okay, shows you the amount of CFCs. Okay, now where do CFCs come from? CFCs come from, again, refrigerants. And so this is just a really cool thing to make refrigerants without ammonia, because ammonia is more dangerous to humans, but as it turns out, the CFC is more dangerous to the atmosphere. And the scientists would say, well, why did they invent this? Well, they actually didn't know that. There was no real reason to study CFCs and their impact against the environment. There was no history at all. There was a completely new revolutionary discovery. But if you look at the red line being up between about 1970 and 1995, that height of that is not good. That means you have a lot of CFCs. Now, actually, there's some similar compounds that you learn more about that are like CFCs, that it come from hairsprays. Yeah, that came from grandma with her big hairdos and spraying them. Those also contribute to holes in the ozone layer. So the red line being up on the graph is not good between about 1970 and 1995. I won't expect you to memorize this graph, but I want you to be aware that there was a point in history where CFCs were at an all-time high that was causing the destruction of ozone. And you can see that if you go down to the bottom graph. And this also is showing some predictions of where the Montreal Protocol people involved in that and the governments think we can really go. If you go to about 2000, you kind of look where things have turned around in terms of the effects of chloride in terms of part per trillion. And that's very, very, part per trillion, again, is very, very small. That's a couple of grains of sand in a wheelbarrow. Okay, so really, really minor impurities there. And so if you notice, the prediction is that it should be able to go down, but that prediction will only hold true if we manage the CFCs that we put into the environment. Okay, so just to read the rest of the verbiage. However, recovery of ozone concentration is slow, with atmospheric chloride concentration not expected to return to the 1980 levels, so known as the 1980 levels, until about 2070, long time out. So it takes so here's the bottom line. It takes a long time for the environment to turn itself around. Okay, the Chapman cycle that generates ozone works very well as long as it's not interfered with by man-made radicals. The natural radicals don't have the catastrophic impact on the ozone layer as those produced by man, because the radicals produced by man will stay in the environment way past those from nature. And that is the problem, that the radicals created in manufacturing, in plants, have a more catastrophic impact on the ozone. And because of the conditions at Antarctica, that's why the hole in the ozone is where it is. It's a perfect laboratory for producing it. So they decided, well, let's try to develop, this brings alternatives to CFCs. The alternative CFCs, halofluorocarbons, replace chloride with halogen to prevent the release of atomic chlorine. When you see the term atomic chlorine, that means radical. Atomic chlorine is a radical. Okay, that means it only has one dot, one electron. It will prefer to. So what it does is it looks around to find somewhere it can attack, so it can satisfy its electron thirst, hunger. So these are better for it. But here's the problem with the HFCs. They're greenhouse gases, okay, which plays a role in the climate change. So you have your wet, which we'll talk about in Chapter 4. So yes, they are better when it comes to ozone protection, but they impact greenhouse gases, and greenhouse gases cause the infrared to be higher. That means it's going to be heat. So the real bottom line here is challenging to find these wonderful organic compounds that we can use in these applications without having some effect on the environment. Therefore, how we regulate them, how we use them, and again, the concentration that we use them in is very, very important to how we can sustain our way of life on this beautiful planet of ours. Right? Now, that brings us back to talking about sunscreens and why we're talking about this. If there's a hole in the ozone, that means it's going to be very important that we develop sunscreens and things of that nature to help protect us from the radiation. Again, UVA and UVB, primarily because UVC is completely filtered out by ozone. But if there's a hole, we're going to start seeing a little bit of UVC coming in. And so this kind of shows you a little bit of diagram of what the diagram on the left shows you what sunscreens look like. But let's read the verbiage first. Sunscreens contain particulates smaller in diameter than the particulate matter discussed in chapter 2. We talked about particulates in chapter 2. And so nanoparticles have dimensions between 1 and 100 nanometers, which are smaller in size to antibodies and small viruses. Now, why is this important? Essentially, what this is talking about, let's see if we can explain it to you a little simpler than reading it. What we're talking about here is that sunscreens have these particulates in them, have these small particles of matter in it that help reflect the UV radiation off the skin. That's the bottom line. And so that's what UV sunscreens are for. And this slide is just really to show you the size of them. Other than that, I really won't be testing you on this slide. But suffice it to say, and maybe I would ask this question, or you should at least know that it's nanoparticles. All right, so let's just settle on that. So if you know that there are nanoparticles in the sunscreen, then I'm going to be happy with this particular slide. This author thought it was very cool to try to show you how small these things were, and it is kind of an exciting part to think about. But beyond that, it's just basically you have nanoparticles dispersed in lotions. You put them on your screen. The UV then does not absorb into your skin, and that's the important thing of how sunscreens work. Okay, they're small enough to allow them to work really well against blocking the UV radiation. So here's how they work. Let's talk about how the particles work. Okay, light absorption by nanoparticles. Most sunscreens contain nanoparticles of zinc oxide and titanium oxide. I always ask this question on my exams, which are able to absorb radiation of certain wavelengths. So that's the bottom line. So we put in this basically zinc and silica, which are small rocks. So these basically nanoparticle rocks, one between less than 100 nanometers. Okay. And when energy is absorbed, electrons are promoted from a lower energy state to an excited state. The energy of radiation has to match or exceed the energy difference between these states in order to for absorption to occur. And that's what happens for zinc oxide and titanium oxide. They work in this regard, and I'll explain to you a little better in just a minute. The energy difference is dependent on the size of the nanoparticles. So they work out the particles so you get this dynamics, where essentially what happens is if you start where, say, ground state, that's where it starts. You get the photons from the sun, that's the sun absorption, and it goes to an excited state, and instead of causing really bad damage, it undergoes heat loss. It's satisfied. So it excites itself, and it breathes with heat loss. So essentially that's what happens. And again, the zinc and titanium have chemical properties based on their position on the periodic table, and not only the position on the periodic table, but their combination with oxygen to make a molecular compound here, a binary compound of zinc oxide and titanium oxide, such that they will absorb it. And you ask, well, how did people figure this out? Well, gee, pretty much scientists tried several ways, and actually it's kind of well known, or at least was known at the time, that these materials had these unique properties when it came to UV. And so someone thought, gee, if they were small enough that they could be in lotions where it wouldn't be gritty on you, and also it wouldn't abrade your skin. Perhaps they would work as UV absorbent. So here's a take-home message for you. Here's a point. One type of material that's used for UV absorption is metal oxides. Specifically, zinc and tin oxide work well. So metal oxides are used. Here's a statement to write down. Metal oxides are used as UV absorbers. Okay? And they absorb the photons. Okay? But there's another area that can be used for UV absorption is organic molecules. Let's back up. Zinc oxide and titanium oxide are inorganic compounds. They're inorganic metal oxides. Okay? Now we come back to light absorption by organic molecules. These are organic molecules. Organic molecules are composed mostly of carbon, hydrogen, and oxygen. And these particular molecules here, some sunscreens contain these organic-based compounds. And they're capable of absorbing UVA and or UVB. Note it didn't say UVC. Why? Because ozone takes care of UVC. So what you notice the top scale on the left side, UVA, UVB. This shows where UVA is from 400 to 320 nanometers, and UVB is 200 to 320 nanometers. Actually, I wish this author had reversed these charts so it would be like we showed in the first one, the electromagnetic spectra. Because you now know that above 400, 400 and 700 is what? Visible. You follow? So UVA is the UVA is closest to the visible range, and then UVB is further away from that. Okay? We know that UVA goes below your skin, right, and sits around and it causes damage over time. UVB zaps your top layer and essentially starts to cause skin cancer on your top layer. And if you're a bald head man, then it's going to affect your scalp as well. So here's the bottom line: we have organic molecules that are capable of absorbing UVA and UVB. That's it. So what do? They formulate these into the lotions along with the titanium oxide and the zinc oxide. So you add zinc oxide and titanium oxide, and you add an organic molecule to it. You add it into a lotion or a spray. You rub it on, and there you have it, UV protection. And you survived Chapter 3 on electromagnetic radiation. Keep in mind, electromagnetic radiation is a natural radiation from the sun producing UVA, UVB, and UVC. UVC is screened out by ozone. Ozone is in the stratosphere and is being regenerated by the Chapman cycle over and over again. But occasionally, industry introduces these bad actors, chlorine radicals, into that. They float around the world until they settle in the polar region, where it's a nice natural laboratory for these radicals attacking ozone and depleting the ozone layer. So therefore, we need sunblocks and sunscreens, and they're composed of UV absorbers from the inorganic family, titanium and zinc, and from organic molecules. There you have it.